Imagine standing in a quiet room, staring at a closed door, and wondering what is on the other side. Except the door was built by the universe. The room was built by the universe. And the very idea of other side was also built by the universe. That is more or less the position we land in when we ask what existed before the Big Bang. It is a question that feels so natural, so obvious, that our brains practically high-five themselves for thinking of it. Yet the universe reacts to this question the way a cat reacts when asked to explain taxes, with a blank stare and a faint air of cosmic mischief. The universe knows something, but it is not telling us easily. And so we are left trying to solve a mystery that might not even be phrased in a way the universe understands. Good evening, curious minds. I truly hope you will enjoy today's video. Before we begin, leave a comment and tell me where and when you're tuning in, and if you find yourself learning something new as you drift towards sleep, consider subscribing. But only if you enjoy these calm journeys through the universe. Now, let's begin. Still, the mystery is irresistible. The Big Bang sits in the cultural imagination as the ultimate beginning, the grand opening line of the cosmic story, the moment when everything, including the idea of moments, sprang into being. But if you are anything like the rest of us curious humans, you cannot help poking at it. If the Big Bang marks the start of everything, then what about the time before that? What was happening then? Was there a then? And if the universe had an origin story, does that mean there was a prequel, the way every franchise eventually reveals some dramatic backstory? It is the kind of question that keeps both cosmologists and late-night thinkers up at night, staring into the dark and imagining that the dark is staring back with a smirk. Asking what existed before the Big Bang is a bit like asking what sound came before the first sound, or what rule existed before the invention of rules, or what software ran before the operating system existed to run software. It is a paradox wrapped in a puzzle, wrapped in the universe's subtle suggestion that we might be using the wrong language entirely. The trouble is that our brains evolved to survive on a planet where before and after are not optional. Something always comes before something else. Breakfast before lunch, sunrise before sunset, regret before promising to never do that again. So when cosmologists suggest that time itself may have begun with the universe, that there may not have been a before in any meaningful way, our brains fumble the concept like someone trying to catch a bar of soap in the shower. But the confusion is part of the fun. Humanity has always lived in a world that makes sense at human scale. We are used to objects being solid, time being steady, and nothing appearing out of nowhere unless it is a pigeon trying to steal a sandwich. Then the universe comes along with its cosmic shrug and shows us that the rules we rely on daily are just local guidelines. Out there, beyond our comforting planet, space stretches, time bends, particles vanish and reappear, and the universe behaves like a brilliant magician who refuses to reveal the trick. It is no wonder that asking about the moment before the Big Bang feels like interrogating a cosmic showman whose only answer is a mysterious wink. Still, we push forward because curiosity is the closest thing humanity has to a superpower. We want to know whether the universe had a trigger, a spark, a hidden chapter tucked behind the cosmic curtain. We want to know whether the Big Bang was a sudden explosion, a smooth beginning, a transition from something else, or simply the part of the story where physics finally became readable to us. And yes, we want to know whether the universe read the instruction manual or whether it skipped straight to improvisation mode, which honestly seems more likely given how creative the cosmos turned out to be. The real thrill of this question is that it forces us into unfamiliar territory. It invites us to step outside the world as we experience it and try to imagine what reality looks like when all the familiar pieces, time, space, energy, matter, the whole cosmic cast, have not yet appeared on stage. It challenges us to think about existence without locations, moments, movement, direction, or cause. It is like trying to picture a story with no characters, no setting, and no plot, yet the story somehow unfolds anyway. And here is the wild part. Despite the strangeness, the question is not pointless. It is not noise. It is one of the most profound questions humans can ask, because baked into it is our longing to understand our place in the universe. Knowing where we came from is deeply tied to knowing who we are. Whether the answer turns out to be a previous universe, a quantum fluctuation, or nothing at all in the way we understand nothing, the search itself expands our minds. Even if the universe refuses to give us a straight answer, chasing that answer helps reveal the hidden architecture of reality. So this chapter begins your journey into the deepest mystery of cosmology, wrapped in wonder and sprinkled with cosmic humor. It is the question that pulls us all in. If the universe started with the Big Bang, then what started the starter? What came before the beginning? And why does the universe keep acting like it misplaced the timeline? Picture a stage so empty, it does not even have a stage. No lights, no props, no backstage crew, not even darkness, because darkness still counts as something. This was the cosmic situation before the Big Bang, not a quiet void, not a shadowy, empty space, but the total absence of anything that could be quiet or shadowy. Then, with absolutely no build-up, no drum roll, and definitely no ticket sales, the universe decided to make its entrance. And what an entrance it was! If cosmic events could win awards, the Big Bang would take home the trophy for Best Opening Scene, because it delivered everything from space to time to the raw ingredients for galaxies in the briefest flash imaginable. The name Big Bang makes it sound like an explosion, but this was not an explosion in the usual sense. Explosions happen somewhere, blasting outward into surrounding space. The Big Bang did not explode into anything. Instead, space itself expanded everywhere all at once. It was the universe's debut performance, and instead of blowing up inside a pre-existing theater, the Big Bang created the theater. The seats, the audience, and the popcorn machine in one go. If that sounds hard to visualize, that is because it is. But it is also what makes it such a spectacular moment in cosmic history. To understand this beginning, imagine the universe as a tiny region packed with unimaginable energy, smaller than anything we can ordinarily describe. Not small like a grain of sand or small like a proton. Those comparisons still involve objects inside a space. At the start, space had not arrived yet. The earliest universe was more like a state of energy so dense and so unified that all the forces we know today, gravity, electromagnetism, and the strong and weak interactions, were fused together into a single, elegant blend. It was the universe before the universe, a moment where everything that would ever become stars or planets or curious humans was squeezed into a state too extreme for our everyday intuition to grasp. Then came the expansion, not a slow stretching or a gentle unfolding, but a rush so rapid that the earliest fractions of a second make even the wildest sci-fi effects look understated. The universe expanded faster than any rocket, faster than any burst of light, faster than anything could move through space, because it was not things moving through space. It was space itself ballooning outward, carrying everything with it. If you could freeze that moment long enough to observe it, you would not see particles zipping around as much as you would see the fabric of reality stretching like a cosmic rubber sheet that just discovered caffeine. As the universe expanded, the dense early energy began to cool. Cooling may sound like a slow, gentle process, but in this context, it was more like watching steam turn to snowflakes in a fraction of a heartbeat. This cooling allowed the first distinctions to form in the previously unified state. Forces separated, particles emerged, energy crystallized into the building blocks of matter. It was like opening a cosmic toolbox and finding that the tools were assembling themselves before your eyes. The early universe was busy, lively, and incredibly productive, even though it still had no stars, no atoms, and definitely no galaxies. The cosmos was only minutes old, yet it was already laying the foundation for everything that would come billions of years later. During these early stages, particles like protons and neutrons took shape, while lighter particles darted around in a hot, glowing haze. The universe resembled a brilliant, blinding fog, so bright and dense that light could not travel freely. Photons kept bumping into charged particles like commuters caught in an eternal rush hour. For hundreds of thousands of years, this glowing fog remained the dominant feature of the cosmos, stretching and cooling, but still too hot for atoms to form. Eventually, the universe cooled enough for electrons to settle into orbits around nuclei, creating the first neutral atoms. When that happened, light was finally free to travel long distances without being scattered. This release of ancient light is still around today, stretched and softened into a faint microwave glow that fills every part of the sky. It is the universe's baby picture, the earliest snapshot we can observe, one taken long after the Big Bang itself, yet still carrying its fingerprints. The true magic of the Big Bang is that it set the rules, energy, and structure of everything we see today, from spiral galaxies to molecules in your coffee to the atoms in your fingertips. It was not simply a moment when things appeared. It was the moment that shaped how everything would behave. If the early expansion had been even slightly different, too fast or too slow, too hot or too uneven, the cosmic story would have unfolded in ways that bear no resemblance to the universe we now inhabit. So when we describe the Big Bang as the universe's dramatic entry moment, that is not poetic exaggeration. It was the grand opening of reality itself, an event without spectators, and yet the reason spectators eventually existed. From a single moment of breathtaking intensity came all the stars that would shine, all the galaxies that would swirl, and all the creatures that would one day look up at the night sky and wonder how it all began. Time is such a constant companion in daily life that we rarely stop to consider what an odd creature it truly is. It marches forward without asking permission. It pulls us across mornings, afternoons, evenings, and the sudden realization that yesterday's breakfast happened 5 years ago. We live inside time the way fish live in water, completely immersed and barely noticing the medium that shapes our entire existence. So when physicists suggest that time itself may have begun with the Big Bang, we are forced to wrestle with something strangely unsettling. The idea that our deepest sense of before and after might not be a built-in feature of reality, but something that flickered into existence when the universe switched on. To understand how radical this is, imagine a world where nothing moves, nothing changes, and nothing ages. If nothing ever changes, then time has no meaning. Measuring time requires events, waves crashing, planets orbiting, or at the very least one lonely particle doing something. But in the earliest stage of the universe, during that first unimaginably small slice of existence, the familiar concept of time had not developed yet. There were no events in the way we usually think of them, no ticking clocks, no flowing sequences. Reality was in a state so strange and unified that the idea of when simply had not been invented. The best way to approach this is not by imagining a clock starting, but by imagining the clock itself being created. When the Big Bang occurred and space began expanding, the structure of time emerged alongside it. Time is woven into the geometry of the universe. It is part of the same cosmic fabric that creates distance, motion, and the very notion of cause and effect. Before that expansion began, there was no cosmic fabric for time to flow through. Asking what happened before the Big Bang is like asking what the neighborhood looked like before the first house was built. It assumes the existence of a street that did not exist yet. This idea comes directly from general relativity, which tells us that space and time form a connected entity, often compared to a flexible sheet. Gravity stretches and curves this sheet, giving rise to the motion of planets and the behavior of light. But this sheet did not exist forever. It had to originate, and the Big Bang marks the boundary where the sheet goes from not existing to existing. The moment the universe expanded into being, so did the timeline along which events would unfold. It is as though a cosmic calendar suddenly printed itself out of pure energy and said, "All right, let us begin." None of this means time is an illusion. You will still age, seasons will still shift, and your coffee will still get cold no matter how passionately you beg it not to. but it does mean that time might not be a fundamental ingredient built into reality from the start. Instead, it might be something that emerged, like a property that only makes sense once the universe grows large enough and structured enough for clocks, whether mechanical, atomic, or biological, to become meaningful. This raises a fascinating puzzle. If time began with the Big Bang, what does that make the Big Bang itself? It becomes not just the beginning of everything physical, but the beginning of beginning. In a very real sense, the universe did not start inside time. Time started inside the universe. This flips our intuition upside down. We are used to thinking in terms of cause and effect, sequences and origins, where one event leads to another. But the origin of the universe may not fit inside that framework. Instead, it might be the framework itself, Trying to imagine a time before time is like trying to imagine turning left at a place that has no directions, or reading a book before it has been written. It makes our mental gears grind because we assume time should work the way it does for us, steady, unstoppable, and always present. Yet physics suggests that time behaves differently depending on the conditions around it. In extreme scenarios, like the Big Bang, time becomes unrecognizable, losing its familiar flow and blending into the chaos of raw, undifferentiated energy. This brings us to the strange question of whether before is even a valid word in the context of cosmic origins. It is a word that depends entirely on time being there first. Without time, before has as much meaning as trying to remember a memory that never happened. You can imagine it. You can try to piece together a picture, but the picture does not correspond to anything real. The universe might not have a before, in the way a flame does not have a shadow. There is simply no place for it to exist. Of course, none of this stops the human mind from trying. Curiosity is stubborn, especially when confronted with a mystery as delicious as the beginning of time. So we develop metaphors, models, and theories that help us explore the edges of understanding. Some physicists compare the Big Bang to the South Pole. You can walk south from any place on Earth, but you cannot walk south of the South Pole. The pole is not just a location, it is the boundary of the definition of south. In the same way, the Big Bang may be the boundary of the definition of before. What makes this chapter so intriguing is that it forces us to rethink not the universe, but ourselves. We are creatures built to navigate time, shaped by its flow, and wired to remember the past and anticipate the future. The idea that time had a starting point challenges us to expand our imagination beyond familiar experience. It invites us to let go of the instinct, to ask what came earlier, and instead accept that the earliest moment might be the moment when earliest first became possible. In the grand cosmic story, the birth of time is not just a chapter. It is the table of contents itself suddenly appearing. And for all our attempts to imagine what lies beyond the first page, the universe gently reminds us that some stories begin only when they begin. To understand how the universe might have emerged from a quantum fluctuation, we first need to talk about the strange realm of quantum physics. the part of reality where the ordinary rules of common sense take one look at the situation, pack their bags, and flee the scene. This is a world where things do not sit still, where particles appear and disappear like shy performers, and where energy behaves as though it has had far too much caffeine. In this microscopic playground, nothingness is not the calm, still void we imagine it to be. It is more like an empty stage where the lights flicker and props occasionally jump out just to keep everyone on their toes. Quantum nothingness is a surprisingly busy place. In classical thinking, nothingness is simple, the absence of matter, energy, space, and time. But in quantum mechanics, nothingness is actually a seething sea of potential, full of restless fluctuations that spontaneously create tiny bursts of energy. These fluctuations happen because quantum fields, the invisible fabrics that underlie all particles, can never quite settle down to perfect stillness. Even at their lowest energy state, they jitter, they twitch, they refuse to behave. And those tiny jitters create brief flashes of energy that blink into existence and then fade out again, often so quickly that calling them momentary feels like an understatement. Now imagine that one of these jittery fluctuations did something unexpected. Instead of fading away as usual, it expanded, it grew, it swelled into something enormous and unstoppable. It is as though one of the universe's smallest hiccups suddenly decided to audition for the role of everything. Picture a cosmic magician stepping onto an empty stage, waving a wand made of pure physics, and producing not a rabbit, but the entire universe, complete with galaxies, atoms, and eventually beings who spend their evenings wondering how the trick was done. This leads to the bold proposition that our entire universe may have begun as one of these quantum fluctuations, a tiny spark of energy, smaller than imagination, briefly surfacing in a quantum vacuum. Only instead of disappearing like it was supposed to, it inflated into the vast cosmic landscape we live in today. If this idea sounds outrageous, welcome to quantum theory, where outrageousness is less a drawback and more a job requirement. Part of what makes this possibility so intriguing is that quantum fluctuations do not need a cause. They happen naturally, automatically, and endlessly. They are built into the very structure of reality. If the universe did arise from such a fluctuation, then its existence may not need a prior trigger. In a sense, the universe might have happened simply because in the quantum arena, happening is something that nothingness does all the time. Of course, the next question practically leaps into our minds. How can something come from nothing? But the quantum version of nothing is not a barren emptiness. It has properties, behavior, and potential. It is like an engine idling at its lowest setting, quietly humming in the background. Even when stripped of everything recognizable, the quantum vacuum is still a stage with underlying structure, and structure, however subtle, can give birth to phenomena. One way to imagine this is to think of a completely still pond. It looks calm from a distance, but on a microscopic level, water molecules are constantly moving, jostling, vibrating. The surface may seem smooth, yet it hides an entire world of ceaseless motion. Likewise, the quantum vacuum looks like nothing from afar, but zoom in far enough and you find continuous activity. And just as ripples can form on the pond's surface if conditions change slightly, a ripple in the quantum vacuum could escalate into something enormous if the circumstances allow it. Another way to think about this is through energy borrowing. In quantum theory, energy can appear briefly as long as it repays itself almost instantly. It is as if the universe allows tiny energy loans, but demands they be paid back within unimaginably short timescales. Most of these loans get repaid without issue. But if some process early in reality's development prevented repayment, say by causing expansion so rapid that the borrowed energy became locked into the structure of space, then you might end up with a universe. A rather large outstanding balance, to be sure, but one that is paid not with interest, but with the existence of everything. The quantum fluctuation idea does not claim to explain every detail of our cosmic birth, but it offers a tantalizing pathway. Maybe the universe began not with a deliberate spark or a mysterious intervention, but simply because the rules of quantum physics allow reality to momentarily try things out. 99 trillion attempts may vanish instantly, but all it takes is one rare fluctuation that expands instead of collapsing, and suddenly you have stars, galaxies, and people putting cereal in the fridge and milk in the cupboard at 3 in the morning. There is something wonderfully poetic about a universe born from a jitter. It suggests a cosmos that did not need an elaborate blueprint or a grand design at the start. Instead, it emerged from the most natural action possible in the quantum landscape, a spontaneous rise of energy from the vacuum. It is the ultimate example of big things coming from small beginnings, and this idea carries a quiet, delightful humor as well. If our universe truly sprang from a quantum fluctuation, then everything, every mountain, every planet, every nebula, ultimately traces back to an event so small and so brief, it almost did not happen at all. It would mean that reality owes its existence to the tiniest possible burst of mischief, a cosmic oops that snowballed into billions of galaxies, a bored magician flicking a glove and accidentally conjuring every atom in existence. In this chapter, we see not a universe with a rigid, solemn beginning, but one that may have originated from the playful jitter at the heart of quantum reality, a subtle tremor in nothingness that set everything in motion. Cosmic inflation is the part of the story where the universe seems to overreact. Imagine a perfectly calm moment, and then, without warning, reality sprints off like it just heard someone unwrap its favorite snack in another room. Inflation describes a period so dramatic and so abrupt that it makes the universe's birth look almost understated. This was not the gentle stretching of space over billions of years. This was a sudden, explosive growth spurt in which the universe expanded faster than light could travel, not because anything outran light, but because space itself was spreading so wildly that light did not have time to keep up. It was the cosmic equivalent of someone tapping the max size button and the universe obliging instantly. To make sense of this expansion, imagine holding a balloon that is barely more than a wrinkled rubber seed. If you breathe into it, the balloon expands gradually. But if you could inflate it in one impossibly fast breath, so rapid that the rubber did not even have time to resist, the balloon would jump in size before your eyes. That is inflation, a moment of runaway expansion where the universe surged outward with such speed that any prior structure, if any structure existed, was wiped clean, smoothed out, scrambled, and erased. It was a clean slate drawn across the cosmos. What caused this sudden burst? Physicists believe inflation was driven by a peculiar form of energy that filled the early universe. This energy had a strange property. Instead of thinning out as the universe expanded, it stayed constant. Most forms of energy spread out and weaken when the space they inhabit grows larger. But this inflationary energy was not interested in following that rule. It acted like a substance that refused to dilute, fueling an expansion that fed on its own consistency. Think of it as a stubborn engine that would not turn off, no matter how fast the vehicle was accelerating. The astonishing part is that this inflationary energy did not need much time to change everything. In an unimaginably tiny fraction of a second, the universe went from a minuscule region smaller than anything we can describe to something large enough that even the fastest particles could not cross from one end to the other. It was an instant makeover on a cosmic scale. If the universe had been a piece of dough, inflation would be the moment it was rolled out into a vast, smooth sheet in one lightning-fast motion. And that smoothness is important. Inflation explains why the universe appears so remarkably uniform on large scales. Distant parts of the cosmos, separated by vast distances, have nearly the same temperature and characteristics, even though they are so far apart that no signal could have traveled between them at the speed of light. Without inflation, this similarity would be baffling. But inflation suggests that all these distant regions were once close neighbors, sharing the same conditions, before being propelled outward faster than any message could catch up. The universe's uniformity is not a coincidence. It is the afterglow of a moment when everything was packed close together, only to be flung apart in a flash. Another striking consequence of inflation is that it magnified tiny quantum fluctuations, minute wiggles in the early fabric of reality, into large-scale features. These tiny initial irregularities became seeds that gravity later amplified into galaxies, clusters, and the vast cosmic web. It is amusing to think that the majestic spiral galaxies we admire today began as microscopic wrinkles stretched across space like patterns on an expanding tapestry. Inflation did not just grow the universe, it planted the blueprint for the structures that would emerge billions of years later. Yet perhaps the most dramatic role of inflation is the way it erased information about anything that might have existed beforehand. If there had been any earlier cosmic events, structures, or conditions, inflation stretched them out so thoroughly that they became indistinguishable. Imagine writing a message on a tiny piece of rubber and then stretching it until the letters smear into invisibility. Inflation does that, but with reality itself. It leaves us with a universe that carries no clear memory of previous states. If something came before inflation, its footprints were whisked away before they could leave lasting marks. This lack of traces is part of what makes inflation both fascinating and frustrating. It answers many questions, yet raises equally compelling ones. If the universe underwent such an intense expansion, it means the earliest moments are hidden behind a kind of cosmic curtain. We can observe what happened after inflation, but the moments before it are concealed by the sheer immensity of the expansion. The universe's earliest secrets may be locked away not by complexity, but by distance. Distance is created so quickly that no information survived. When inflation eventually ended, the energy driving it decayed into a hot, dense soup of particles, marking the beginning of the more familiar cosmic evolution. But the universe, still buzzing from its enormous growth spurt, retained the structure that inflation left behind. Space was vast, smooth, and waiting for matter to gather into stars and galaxies. Inflation set the stage so thoroughly that everything which followed, every cluster, every nebula, every swirling cloud of stardust, unfolded within a universe that had already been sculpted in advance. Cosmic inflation is not just a wild moment in the universe's youth. It is the event that shaped the stage on which cosmic history unfolded. It smoothed the chaos, stretched the fabric of space to impossible sizes, and left behind a universe ready to grow into the strange and wonderful place we explore today. It was the universe's startled balloon moment, swift, dramatic, and unmistakably transformative. If cosmic inflation was the universe dramatically sprinting outward, the bouncing universe theory imagines something entirely different. A cosmos caught in an endless rhythm, expanding and contracting over and over in a kind of grand cosmic breathing exercise. Instead of a single beginning, this idea paints a picture of a universe that has been through multiple lifetimes, each ending with a collapse inward before rebounding outward again. The metaphor of a cosmic accordion fits perfectly here. Each expansion stretches the cosmic fabric, and each contraction squeezes it back in, only for the next expansion to begin anew, as if the universe inhaled, exhaled, and then decided to repeat the cycle for dramatic effect. To understand this vision, imagine space not as a static arena where events happen, but as a dynamic performer with moods and movements. In this theory, the universe one day stops expanding and begins to feel the pull of everything it contains: galaxies, planets, energy, light. All of it contributes to the gravitational tug that slowly but surely reverses the direction of cosmic motion. Instead of stretching, the universe begins to shrink, not abruptly, not violently, but steadily, like a great cosmic tide turning. Over unimaginable periods of time, everything draws closer together, and the distances between galaxies narrow. The night sky would grow brighter, not darker, because everything would be crowding back into a more compact configuration. During this process, the The universe does not merely compress objects, it compresses space itself. Regions that once flung themselves apart now move toward one another, and the large-scale structure of the cosmos starts to fold inward. Gravity becomes the star of the show here, pulling more and more forcefully as the universe contracts. Eventually, everything that had once been distributed across billions of light years begins concentrating toward a smaller and smaller region. As this collapse deepens, conditions become hotter, denser, and more extreme. The cosmic accordion pulls tighter and tighter, heading toward a state that mirrors the intensity of the earliest universe, but reached from the opposite direction. This contracting phase is sometimes described as the Big Crunch, a dramatic-sounding but conceptually straightforward moment when the universe collapses to a state of extreme density. But the bouncing universe theory does not end at this crunch. Instead, it suggests that the collapse triggers a rebound, a reversal, where the universe cannot compress any further and ricochets outward in a massive bounce. This rebound becomes, in effect, the new expansion phase. Instead of a universe that began from absolute nothingness, this model proposes a universe that was reborn from the remains of its earlier self. A helpful way to picture this is to imagine a ball dropped onto a trampoline. As it falls, it accelerates downward, compressing the trampoline surface. At the moment of maximum compression, the downward motion stops entirely, only to reverse as the tension in the trampoline launches the ball back upward. In the bouncing universe model, the cosmos behaves similarly. Gravity pulls everything inward until the pressure and density reach a point where the collapse cannot continue. At this moment, something deep in the laws of physics pushes back, triggering a rebound that becomes the next cosmic expansion. Some versions of this theory turn to quantum gravity for an explanation of how the rebound works. At extremely small scales, quantum effects could prevent the universe from reaching an actual point of infinite density. Instead, quantum rules might make space itself resistant to being crushed too far, creating a kind of built-in resilience. When the universe becomes tiny enough, these quantum effects could produce a counteracting force, preventing a complete meltdown of physical laws and enabling the bounce. In this interpretation, the bounce is not a glitch or an accident, but a natural outcome of how space behaves at its smallest and most fundamental level. What makes the bouncing universe theory so intriguing is that it offers continuity. Instead of imagining the birth of the cosmos as a one-time event without precedent, we can imagine a sequence of cosmic cycles. Each cycle has its own story, its own expansion, its own galaxies, perhaps even its own forms of life. Our universe could be just one chapter in a much longer, ever-repeating epic. The previous universe, and the one before that, and the one before that, may each have had their own histories, though all evidence of them was erased in the crushing and bouncing process, leaving no clear memory except the momentum of the cycles themselves. This raises an almost poetic question. If universes rise and fall in endless succession, does the cosmos learn anything from the cycles, or does it simply reset each time, unaware that it has lived this pattern before? The universe does not leave notes for its future selves, because all information is shattered and scrambled at the crunch. Every cycle is a clean slate, a new chance, a fresh cosmic breath. Another fascinating aspect is the possibility that each bounce could produce different conditions. Maybe some cycles expand faster or slower, or create different mixtures of matter and energy. Maybe some cycles last longer than others. The bouncing universe is not required to be perfectly repetitive. It can vary slightly with each rebound, like a cosmic heartbeat that never beats exactly the same way twice. In some versions, the cycles stretch over longer periods with each rebound, gradually changing the overall pattern. In others, the rhythm is steady and eternal. While this idea does not have definitive experimental proof, it captivates the imagination because it reframes our place in the cosmic story. Instead of being children of a single beginning, we might be descendants of an entire lineage of universes, each one giving rise to the next. The rebound that created our universe could have been fueled by the collapse of a universe long vanished, one whose stars shone and faded before ours ever existed. In the bouncing universe theory, the cosmos is not a singular event, but a symphony of expansions and contractions, a rhythm that may echo forever. It is the grand accordion of reality, endlessly compressing and rebounding, playing a cosmic tune older than time as we know it. The notion of a cyclic universe is one of the most dramatic, poetic, and strangely comforting possibilities in cosmology. Instead of imagining our universe as a single, fragile, one-time event, this idea envisions reality as an eternal storyteller, one that finishes a tale, clears its throat, and begins again with a brand new narrative. It is as if the cosmos has a habit of restarting itself whenever the plot becomes too tangled, too stretched, or too unstable for further development. In this view, the universe is not a one-off miracle, but a recurring performance with infinite acts. To appreciate the cyclic concept, imagine the universe as a vast stage that resets after each show. One cosmic cycle ends, the curtains fall, and the set collapses. But instead of leaving the stage empty forever, new scenery is assembled, new characters appear, and the next show begins. Each cycle is independent, yet all are connected by the underlying stage itself, the fabric of space and time, capable of rebuilding and reshaping itself endlessly. Cyclic models explore many different versions of how such reboots might happen. One of the core ideas is that the universe undergoes phases. Long ages of expansion followed by transitions that lead into a contraction or transformation, which then triggers the next round of expansion. Unlike a simple bouncing universe where the cosmos shrinks and rebounds in a straightforward motion, cyclic models often involve richer steps: cooling, warming, stretching, flattening, reshaping, smoothing, and eventually resetting in ways that leave the next cycle primed for its own evolution. One version imagines the universe gradually spreading out over inconceivably long durations, with galaxies moving farther apart until everything becomes cold, sparse, and deeply isolated. Stars extinguish themselves, black holes evaporate, matter thins into a faint haze. The universe becomes so stretched that it no longer resembles the vibrant place it once was, a quiet cosmic desert where expansion has outpaced everything else. But instead of ending there, this thinning stage becomes the beginning of renewal. Hidden mechanisms in the underlying cosmic fabric could push the universe into a new phase, compressing or reconfiguring space until conditions ripen for the next beginning. Another variation of the cyclic idea does not require the universe to collapse at all. Instead, it proposes that expansion itself can trigger the next cosmic cycle. Imagine space stretching so much that new regions form naturally, slipping into their own expansions, almost like budding branches on a cosmic tree. Each branch becomes a new universe, distinct yet born from the same underlying process. In this scenario, cycles unfold not in a single repeating chain, but as generations of universes spawning new ones in a continuous lineage. Then there are models that propose a grand reset long before expansion slows or stops. As space spreads, certain physical conditions drift toward states that can no longer support a stable cosmos. Instead of collapsing, the universe might undergo a sudden shift, something like a cosmic phase transition. You can picture this as water freezing or boiling, except on a scale where the very rules of existence change their form. When this transition hits a critical point, the old cosmic order dissolves, and the universe reorganizes itself. The transformation wipes away old information, scrambles structures, and sets the foundations for the next cycle. It becomes not a collapse, but a retuning of existence. What makes cyclic theories especially captivating is that they treat the universe not as a fragile accident, but as a resilient system with built-in renewal. In these models, the universe is not destined to drift toward a lifeless ending. Instead, it has a natural tendency to restart itself, like a cosmic phoenix rising from the ashes of its prior form. Each cycle offers a fresh beginning, not bound by the remnants of the previous cycle, because the transition cleanses the slate. Memory does not carry over. No galaxies survive to wave hello to the next universe. Each cycle forms its own stars, its own chemistry, its own patterns, and perhaps its own civilizations that look out at their night skies and imagine they are living in the first and only universe ever made. A particularly intriguing aspect is how cyclic models reframe the idea of time. In a single beginning universe, time has a clear direction. It starts, it moves forward, and it marches toward an end. But in a cyclic universe, time may not have a true beginning or conclusion. It becomes a loop, or in some models, an infinite spiral where each cycle is slightly different from the last. Time may be layered, with cycles stacked atop one another, like chapters in a book that never ends. The universe gains a sense of continuity, not through unbroken existence, but through repeated renewal. Cyclic theories also spark philosophical wonder. If the universe endlessly recreates itself, could there be echoes across cycles? Not in the physical sense, each cycle loses almost all memory of the prior one, but perhaps in the patterns or tendencies that emerge. Maybe each cycle grows structures of similar scale or complexity, not because they are copied from before, but because the mechanics of physics naturally lead to such shapes again and again. If so, the universe may be rewriting itself endlessly, using the same cosmic grammar to tell entirely new stories. The allure of cyclic ideas lies in how they stretch imagination beyond the singular. Instead of one universe with one birth, we get a cosmic saga, an eternity of breaths, beats, and transformations. The universe becomes a seasoned storyteller, always ready for its next performance, always prepared to rebuild itself out of its own remnants or transitions. In this vision, the cosmos is not just a place with a beginning. It is a rhythm, a pattern, a sequence of rebirths, endlessly unfolding as though the universe simply refuses to stop the show. The ekpyrotic model invites us to step far outside the familiar three-dimensional comfort zone and wander into a realm where reality is built from layers, vast, flexible sheets of existence known as branes. These branes are not surfaces in ordinary space, but colossal structures floating in higher dimensional territory. In this picture, our entire universe sits upon one such brane, stretching out like an enormous cosmic continent, suspended in an ocean of dimensions we never see. And according to this idea, the Big Bang may not have been the beginning of everything, but the dramatic result of two such branes smashing into each other with all the subtlety of an interdimensional fender-bender. To appreciate this model, imagine our universe as a gigantic four-dimensional trampoline. Everything we know, stars, particles, pizza, and thoughts, lives on the surface of this trampoline. Now imagine another trampoline floating parallel to ours, separated by a tiny sliver of a dimension we cannot access or perceive. The separation is so small that, from our perspective, it might as well be zero. Yet these branes remain distinct, like two pages pressed together in a book. They do not merge, but they coexist within a larger dimensional space, each carrying its own version of reality. The ekpyrotic idea suggests that these branes are not always peacefully aligned. Over unimaginable stretches of time, they drift, ripple, or move according to the mysterious dynamics of higher dimensional physics. And sometimes, just sometimes, they collide. Not gently, mind you. A brane collision is not a soft handshake. It is a cosmic impact of staggering magnitude. When our brain smacked into another, the energy released created what we perceive as the Big Bang, a burst of heat, expansion, and radiation that set our universe ablaze with activity. The collision did not create space, because the brain was already an arena for existence. Instead, it woke up the universe, igniting the energy that would eventually condense into matter and fuel billions of years of cosmic evolution. What makes this model so fascinating is that it reframes the Big Bang not as a beginning, but as an event, a transformational moment, rather than the origin of all space and time. The branes themselves existed before the collision, quietly drifting in a higher dimensional environment. The impact was simply the moment when their motion created a violent burst of energy in our brain's fabric, lighting the spark for the universe we inhabit. This allows the ekpyrotic model to sidestep the philosophical puzzle of something emerging from nothing. Instead, something happened because something else bumped into it. An explanation that feels surprisingly relatable for such an exotic idea. The term ekpyrotic comes from an ancient Greek word meaning conflagration, a reference to old philosophical ideas where the cosmos occasionally burned and renewed itself. And fittingly, the modern ekpyrotic model offers a universe born from heat and shock, an immense cosmic fireball triggered by branes colliding like titanic plates of reality shifting in a multidimensional landscape. It is a dramatic origin story, full of movement and tension, not the serene beginning sometimes imagined. A remarkable aspect of this idea is the role texture and ripples play in the branes. According to the theory, branes are not perfectly smooth. They carry subtle waves, distortions, and undulations, much like the faint ripples on the surface of a lake. When two branes collide, these ripples determine where energy concentrates. Some regions collide slightly earlier, some slightly later, creating small variations in density across the newly ignited universe. These tiny differences become the seeds from which cosmic structure grows. Galaxies, clusters, voids. These immense patterns may trace their origins not to quantum randomness, but to the pre-existing wrinkles on the branes before collision. It is like discovering that the entire cosmic architecture owes its shape to drapery patterns on the universe's curtains. Another captivating element is the role played by extra dimensions. In our everyday experience, we move through length, width, and height. Time adds a fourth dimension, charting our journey from past to future. But in the ekpyrotic model, there may be additional dimensions beyond these, not small, curled up ones like those proposed in some other theories, but large, extended dimensions that separate branes from one another. These extra dimensions are not places we can visit, but gaps between branes that hold the potential for cosmic interaction. They give the universe depth in directions we cannot perceive, like a vast backstage hidden behind the main stage of observable reality. This raises intriguing questions about what space truly means. If our universe is just one brane among many, does that mean reality is like an enormous stack of papers, each sheet a separate universe with its own physics? Could branes drift apart, collide again, or produce repeated cycles of cosmic ignition? Some versions of the ekpyrotic idea suggest that brane collisions could happen periodically, creating a rhythmic pattern of births and renewals. In that sense, our universe may be part of a long lineage of brane cycles, each collision generating a new cosmic epoch with distinct properties. One of the most charming, if slightly unsettling aspects of this model is how casually it treats the crushing event that birthed everything we know. A brane collision sounds cataclysmic from our perspective, but in the higher dimensional world, it might be as natural and routine as tectonic plates drifting and bumping into each other. To the branes, it could be just another day in their cosmic commute. Meanwhile, to us, The event was the dramatic flash that sculpted all matter, all energy, and eventually every spark of intelligence capable of contemplating the event in the first place. The ekpyrotic model does not claim to have all the answers. It offers a daring alternative to the traditional picture, one that replaces singular beginnings with dynamic encounters. It enriches the story of the universe's origin with motion, dimension, and grand collisions in a realm just beyond our reach. Whether or not it ultimately describes our true cosmic heritage, the model expands our imagination and challenges us to consider that the universe's birth may have been part of a larger dance, a dance of branes drifting in unseen dimensions until their paths crossed and reality burst into flame. The multiverse idea is one of those concepts that starts out sounding like pure science fiction and then slowly, unsettlingly, begins to feel almost reasonable. Instead of a single universe, our universe, this idea imagines an enormous, possibly infinite expanse where countless universes float like bubbles drifting in an endless cosmic sea. Each bubble would be a complete universe with its own space, time, and physical rules. Some might be dangerously chaotic, others might be eerily calm, and some might be so strange that our minds would tie themselves in knots, trying to comprehend how anything could form within them at all. If our universe has a cosmic personality, then the multiverse suggests it may be just one character in an infinite ensemble cast. To visualize this, imagine a pot of simmering water. Tiny bubbles continually form, grow, separate, and dissolve. Now replace the pot with an endless expanse of space, and instead of water, imagine a vast energy-filled field bubbling with potential. Each bubble that forms is a universe, self-contained, sealed off, expanding internally, and unable to interact with its bubble neighbors in any meaningful way. Our universe is one such bubble, floating, expanding, and carrying billions of galaxies inside it like luminous dust motes. One version of the multiverse idea proposes that this bubbling process is driven by the underlying energy of reality, which can spontaneously generate new universes the way sparks fly from a grinding wheel. Most sparks fade instantly, but occasionally one lasts, growing, stabilizing, and expanding. That spark becomes a universe. What makes this possibility wild is the thought that there may be no limit to how often this happens. New universes could be budding off constantly, each one forming with its own conditions, its own underlying rules, and its own cosmic destiny. But this bubbling picture is only the beginning. There are versions of the multiverse where universes do not merely differ in size or shape. They differ in the very foundations of physics. For example, in our universe, the forces of nature have very particular strengths. Gravity is gentle rather than crushing. Light moves at a specific speed. Atomic particles cooperate in ways that allow stars to form and atoms to be stable. But in another universe, those constants might be completely different. Imagine a universe where gravity is so strong that everything collapses instantly, or so weak that matter cannot clump together at all. Or picture one where the speed of light is radically slower, creating a cosmos that unfolds in glacial slow motion. These universes might be barren, chaotic, or so alien that even imagining them feels like trying to dream in a language you have never heard. Some multiverse ideas go even further, suggesting that universes might emerge with completely different logic. Space might have more than 3 dimensions. Time might behave like a loop instead of a line. Particles might follow rules that make no sense to us, because our understanding is shaped entirely by this universe's playbook. In that sense, our universe is not the standard model. It is simply one version among an unimaginable variety, each version a roll of cosmic dice. What makes this concept especially intriguing is how it reframes our sense of cosmic specialness. For centuries, humans believed Earth was the center of everything. Then we learned it was just one planet among many. Then we discovered our star was one among billions in our galaxy one among trillions in the observable universe. And now, the multiverse suggests that even our entire universe might be just one bubble among countless others. The multiverse is the universe's way of saying, you are special, but also, not that special. Yet there is something oddly comforting about that scale. If universes are plentiful, then reality becomes even grander than we imagined. The existence of so many cosmic possibilities means that nature is endlessly creative, endlessly experimenting. Our universe might be just one successful recipe among many attempts, each universe mixing its ingredients of energy, matter, and physical laws in different proportions. Most combinations would produce nothing stable, nothing long-lived. But every now and then, the right blend occurs, and a universe like ours unfolds, gradually decorating itself with stars, planets, chemistry, and eventually beings curious enough to contemplate all of this. Another compelling aspect is how the multiverse might explain the strange perfection of our cosmos. When scientists look at our universe, they notice that many physical constants seem just right for life to exist. It is like walking into a room where every knob and switch has been tuned to exactly the correct setting. Instead of assuming that someone set the controls deliberately, the multiverse suggests that there are countless rooms, each with different settings. We find ourselves in this particular universe not because it was designed for us, but because it is one of the few where beings like us can arise at all. In the other universes, those with wild, incompatible settings, life never had a chance to wonder about the knobs. But perhaps the most mind-bending part of the multiverse is that we may never be able to visit or observe any other universe directly. The walls of each bubble are, in a sense, sealed. Space inside a bubble is expanding, pushing everything apart, while the space outside it belongs to a different universe entirely. There may be no bridge, no tunnel, no cosmic back door. The very structure of reality keeps each universe isolated, like islands separated by uncrossable oceans. Even so, the multiverse refuses to let our imaginations rest. It hints that reality might be far larger than the universe we see. It suggests that behind the cosmic horizon lie not just galaxies we cannot reach, but entire universes we cannot even access. The multiverse widens the stage of existence so dramatically that thinking about it is almost like staring into a funhouse mirror that reflects endless versions of reality stretching into forever. In this chapter, the universe becomes not the whole story, but a chapter in a cosmic anthology, a single bubble drifting in a sea of other bubbles, each with its own quirks and cosmic personality. The multiverse invites us to imagine reality as richer, stranger, and more varied than anything found in our own cosmic backyard. The no-boundary proposal is one of those ideas that takes your most basic intuition about beginnings, folds it neatly, and tosses it out the nearest window. We are used to things starting somewhere. Stories begin on the first page. Lives begin with a first breath. Even a loaf of bread begins with dough and a hope that you remembered the yeast. But according to the no-boundary proposal, the universe itself may not have begun in any traditional sense. Instead, its earliest state might resemble the smooth, continuous surface of a sphere, a cosmos with no edge, no corner, no abrupt starting point, where everything suddenly switched on. It is as though the universe politely decided to exist without ever going through the awkward "this is the first moment of everything" phase. To understand this idea, picture a globe. You can walk north or south, east or west, and at no point do you encounter a sign that says, "You have reached the edge of the earth. Please turn around." The surface has no boundary. It is finite. Yet its continuity means that there is no special point where the surface begins or ends. The no-boundary proposal suggests that the universe's earliest moment is like that, smooth, rounded, continuous, and free of the singularity that classical cosmology once predicted at the beginning of time. This view emerges from merging quantum mechanics with general relativity, two powerful theories that often disagree like siblings arguing about whose turn it is to do the dishes. When pushed to extremes, such as the conditions near what would traditionally be called the Big Bang, the two frameworks clash. Relativity predicts infinite density, infinite temperature, infinite everything. Quantum mechanics, however, steps in and says, "Hold on, nature does not do infinity. There must be a different shape to this beginning." The no-boundary proposal offers that shape. According to this idea, the universe transitions smoothly from a timeless state into what we now experience as time flowing forward. That earliest state is not a moment in time, but something more like a region where time behaves differently, so differently, in fact, that usual concepts like before and after simply do not apply. It is like trying to use a clock to measure the warmth of sunlight. The tool does not match the phenomenon. One way to picture this is to imagine the early universe as a rounded, four-dimensional structure. While we cannot visualize four dimensions directly, we can grasp the analogy. At the smallest scales, time behaves like a spatial dimension. Just as the surface of a globe curves smoothly without an edge, the early universe curves through a region where the distinction between space and time becomes blurry. The universe is not emerging from an edge or a point. Instead, it transitions from a state without boundaries into the expanding cosmos we know. This means there was no dramatic instant where the universe began from nothing. no cosmic spark, no sudden eruption from an infinitesimal point. Instead, the universe gently emerged like a sunrise that does not snap into existence, but slowly brightens the horizon. The transition from a boundaryless region into a universe with time, space, and structure is continuous, a cosmic dawn rather than a cosmic explosion. One beautiful aspect of the no-boundary proposal is the way it handles the concept of beginning. Instead of viewing the universe as a story with a first sentence, it treats the early state more like the rounded bottom of a bowl. Everything rests upon that curve. But the curve itself does not require a starting corner. It is simply the shape of how the universe is structured at the smallest scales. Nothing needs to be inserted from outside. Nothing needs to ignite. The universe unfolds naturally from this geometry, much the way a flower unfurls from a bud without needing a spark to tell it how. This proposal also suggests that the earliest universe was smooth and simple, far more ordered than the chaotic scene you might imagine at the dawn of everything. That simplicity arises because the no-boundary condition does not allow abrupt changes or jagged edges. The fabric of reality begins in the smoothest state possible, and complexity emerges only as the universe expands, cools, and evolves. The early cosmos, under this view, is not a battlefield, but a quiet, rounded beginning stage. Another engaging aspect of this idea is the way it reframes the question of why the universe is the way it is. If the universe had a sharp origin or spontaneous beginning, one might wonder what special conditions triggered that moment. But if the universe has no boundary, if its beginning is simply the rounded shape of space-time, then the cosmos does not need external justification for existing. Existence becomes the natural consequence of geometry. This is one of those moments when physics quietly blends into philosophy, offering a view of reality where the question, "Why is there something rather than nothing?" becomes less puzzling because the universe never needed a dramatic starting signal in the first place. Perhaps the most delightful part of the no-boundary proposal is how elegantly it avoids paradoxes. When people ask what came before the universe, the answer here is simple. Before does not exist in the way we think it does. Asking what came before the boundaryless region is like asking what is south of the South Pole. The question assumes a direction that simply stops being meaningful when you reach a certain point. In this sense, the no-boundary proposal does not just redefine the beginning, it dissolves it. Even though the idea is bold and deeply counterintuitive, it carries a quiet simplicity. It says that the universe may not have sprung from a singular point of infinite density, nor from an external cause, nor from a collision, nor from a previous cycle. Instead, space-time itself may have flowed naturally out of a smooth, curved region without edges, no boundary, no edge, no cliff where reality suddenly decides to exist. In this chapter, the beginning of the universe becomes not an explosion, not a bounce, not a rupture, but a gentle curve, a seamless unfolding from a region where time and space were intertwined in a smooth geometric embrace. The cosmos does not start with a bang. It begins with a graceful, continuous sweep, like a globe with no point where everything suddenly starts and nothing exists to fall off. When we picture empty space, we tend to imagine a quiet, peaceful nothingness, a blank cosmic room where absolutely nothing is going on, a serene desert, a silent void, the universe's do not disturb sign. But in modern physics, empty space is anything but tranquil. Instead, it behaves more like a restless cauldron simmering with invisible activity, a kind of cosmic stew where energy bubbles and flickers even when no particles are around to stir it. This mysterious, ever-present energy is known as vacuum energy, and it challenges the entire idea that nothing is truly nothing. In fact, vacuum energy suggests that before particles, before atoms, before anything recognizable existed, space itself may have been brimming with potential, teeming with jittery energy that refused to sit still. To understand why empty space is so lively, we need to peer into the quantum rules that govern reality on the smallest scales. Quantum mechanics has a bit of a reputation for being the universe's mischief maker, constantly disobeying classical expectations. One of its most dramatic declarations is that fields, these invisible fabrics pervading all of space, can never fully calm down. Even when they have no particles, no waves, no excitations, they still buzz faintly with leftover energy. You can think of this energy as the cosmic equivalent of static electricity that never fully discharges. The vacuum hums, vibrates, and produces tiny, brief pulses of energy that appear and vanish like impatient sparks. The term vacuum energy might sound like an oxymoron. How can a vacuum, a region free of things, have energy? But in quantum physics, the vacuum is not an absence of stuff. It is a presence of possibilities. It is a background field with a lowest possible energy state, a state that still refuses to be perfectly still. Even if you remove every atom, every photon, every speck of matter from a region, the vacuum remains, humming away with its zero-point energy, always on the brink of producing brief fluctuations. These fluctuations are so intrinsic to space that they cannot be switched off. They occur because the quantum fields that fill space cannot sit motionless. They jitter spontaneously, much like someone who has had far too much coffee and tries in vain to hold perfectly still. This jitter is not caused by anything. It is built into the nature of quantum fields themselves. It is a kind of irreducible activity, a baseline hum that permeates the universe. Long before particles formed, this vacuum energy may have dominated the character of the universe. Imagine a cosmos with no atoms, no light, no structure, just an expanse of raw potential pulsing with invisible fluctuations. In such an environment, the vacuum energy would set the stage for everything that followed. As space expanded and cooled, this energy could give rise to the first excitations of the fields, which would eventually become the first particles. In that sense, matter may not have been the starting point of the universe, but the after effect of a deeper, more fundamental energy that had been present all along. One of the fascinating aspects of vacuum energy is its relationship to pressure. Unlike regular energy that tends to dilute as it spreads, vacuum energy behaves strangely. It exerts a kind of negative pressure. Picture a pressure that does not compress or push outward in a normal way, but instead encourages expansion. It is as though vacuum energy is constantly nudging space to stretch, gently urging the universe to grow larger even when nothing seems to be happening. This mysterious behavior is tied to the expansion of the cosmos today, suggesting that vacuum energy still plays a major role in shaping the universe's overall evolution. The idea that vacuum energy existed before particles is important not just for physics, but for the philosophical understanding of what before might even mean. When people ask what existed prior to matter, or what filled the universe before anything physically recognizable appeared, vacuum energy offers a surprising answer. Space itself is never truly empty. It always carries a restless undercurrent of activity, even when stripped to its barest form. This means that the primordial universe was not quiet or passive. It was an arena of energetic potential, a roiling backdrop where the seeds of matter could eventually emerge. What makes vacuum energy so captivating is how understated it is. You cannot see it, you cannot touch it, you cannot bottle it like some cosmic potion, but its effects are everywhere. It affects how particles behave. It influences the expansion of the universe. It shapes how fields settle into stable configurations. It whispers quietly beneath every physical interaction, an invisible conductor guiding the cosmic orchestra from behind the scenes. Another intriguing implication is the possibility that vacuum energy varies under different conditions. In the early universe, it might have been higher, influencing cosmic behavior in ways we can only infer. As the universe expands, this energy could shift or evolve, altering the environment where structures form. In some theories, different regions of reality might have different vacuum energy levels entirely, giving rise to universes with distinct physical properties. Within our own universe, vacuum energy remains constant enough to be subtle, but powerful enough to guide cosmic expansion. Perhaps the most poetic aspect of vacuum energy is the notion that existence emerged not from silence, but from background murmurs. The vacuum did not sit idly waiting for particles to appear. Instead, it was alive with energy, guiding the emergence of particles when the conditions became right. The universe's earliest moments, in this light, were shaped not by objects, but by the restless potential of space itself. In this chapter, the universe is not a place that began empty and became full. It began with fullness of a different kind, a fullness of energy rather than matter. Before particles, before atoms, before the first spark of light, reality was a simmering ocean of vacuum energy, seething gently in the shadows of the quantum fabric. It was a universe waiting to unfold, rich not with substance, but with pure potential. There is a moment in the history of the universe when everything humans understand about physics begins to wobble, crack, and eventually give up entirely. a moment so dense, so energetic, so compact that the laws we rely on, those elegant equations that describe planets, particles, and the beating of atomic clocks, simply do not apply. This is the realm where classical ideas of space and time break down, and where quantum rules, normally so subtle and delicate, must somehow govern the behavior of the entire cosmos. Enter quantum gravity, the ambitious, rebellious branch of physics that aims to merge the cosmic order of general relativity with the jittery unpredictability of quantum mechanics. If the universe were a story, quantum gravity would be the chapter titled "When the Plot Became Too Complicated and New Grammar Had to Be Invented." To appreciate why quantum gravity matters, picture general relativity and quantum mechanics as two brilliant but extremely stubborn geniuses. Relativity explains the large-scale universe, galaxies curving space, black holes bending time, planets following geodesic paths like dancers on a warped floor. It is smooth, geometric, and surprisingly graceful. Quantum mechanics, on the other hand, rules the small-scale realm, electrons jumping between levels, particles vibrating like nervous teenagers, and uncertainty woven into the fabric of everything. It is chaotic, twitchy, and fundamentally probabilistic. Individually, each theory works beautifully. Relativity handles the cosmic giant stuff. Quantum mechanics handles the tiny jittery stuff. And both do their jobs flawlessly until you push them into the same room and ask them to cooperate. Then they behave like rival chefs arguing about who gets to run the kitchen. Where these theories clash most dramatically is at density and energy extremes, such as the earliest stage of the universe. Whenever the universe becomes too compressed, the smooth curves of relativity collide with the graininess of quantum mechanics. The result is mathematical chaos. Infinities erupt, equations misfire, and physics starts producing nonsense, like predictions that space shrinks to zero while energy shoots to infinity. It is not so much a breakdown as a cosmic meltdown. Quantum gravity aims to fix this by inventing a unified language that describes both gravity and quantum behavior simultaneously. It is a monumental task. Gravity in relativity is not a force, but the curvature of space-time itself. But quantum mechanics treats forces as exchanges of particles, flickering packets of energy passed back and forth. How do you quantize space-time? How do you treat space? Not just objects in space, but space itself, as something that can jitter, wiggle, and fluctuate. This is like trying to make the stage perform the same dance as the actors. One of the core goals of quantum gravity is to reveal the true nature of space-time at the smallest possible scales. Relativity imagines space as a smooth fabric. Quantum gravity suggests that this smoothness is an illusion, like a picture on a screen that looks seamless until you zoom in far enough to see the pixels. At unimaginably tiny scales, space-time may be grainy, foamy, or composed of discrete units that snap together like Lego blocks of geometry. Instead of a continuous expanse, space might be made of tiny quanta, each a minuscule chunk of volume or area. time might have similar quantized steps rather than flowing continuously like water. This granular vision of space-time becomes especially important when thinking about extreme density. In the very early universe, everything was crammed into such a tiny region that the smallest details of space-time mattered. If space came in tiny chunks and time came in tiny ticks, then the universe's birth would not be a smooth explosion from an elegant singularity. It would be a quantum transition governed by probabilities, fluctuations, and the discrete nature of space-time itself. The impossible infinities predicted by classical relativity would vanish, replaced by quantized structures that refuse to collapse into zero size. Different approaches to quantum gravity imagine these building blocks differently. Some theories picture a network where nodes and links define the geometry of space, almost like a cosmic web woven from threads of pure math. Others imagine vibrating entities or loops that stitch together to create distance and curvature. In all these ideas, the essential point remains: at the earliest stages, space itself did not behave normally. It shimmered, quivered, and responded to quantum rules as if the entire universe were a single, all-encompassing particle. This quantum behavior of space-time could also influence the universe's expansion. Relativity predicts how space stretches and curves, but quantum rules would add randomness, small variations, and fluctuations that subtly shape the early universe's structure. These fluctuations might guide how the first directions, dimensions, and patterns appeared. The large-scale arrangement of cosmic features, those giant webs of galaxies we see today, could be distant echoes of quantum ripples imprinted on space-time itself during its earliest, densest moments. Quantum gravity also invites us to rethink what we mean by beginning. If space-time has a discrete structure, then the universe may never have reached an actual singularity. Instead of shrinking to a point where physics collapses, the cosmos might have reached a minimum size, a kind of quantum floor that prevents total collapse. This opens the door to scenarios where the universe transitions smoothly from one phase to another without facing impossible infinities. The earliest universe becomes a place where geometry becomes probabilistic, where the flow of time becomes fuzzy, and where the very shape of space obeys rules we have not yet decoded. Perhaps the most profound implication of quantum gravity is not a specific prediction, but a shift in perspective. It suggests that space-time is not a passive background, but a dynamic participant. At extreme densities, space is not a silent container. It is an active entity vibrating with quantum uncertainty. Time is not a steady arrow. It may flicker or blur under certain conditions. Physics becomes not a description of things happening in space and time, but a description of space and time themselves behaving as quantum objects. In this chapter, the universe's earliest state ceases to be a broken endpoint where physics fails. Instead, it becomes a frontier, a place where new rules dominate, where gravity dances to a quantum rhythm, and where the deepest mysteries of existence are woven into the very fabric of space-time. Quantum gravity does not just rewrite physics. it rewrites the stage upon which physics plays its entire cosmic drama. There is something irresistibly human about wanting to trace every story back to its very first moment. We look at a finished puzzle and want to know who opened the box. We hear a melody and wonder who played the first note. So when we point our curiosity at the universe, it feels natural, almost required, to ask what happened before it began. But philosophers and cosmologists have long suspected that this question may be less about the universe and more about the way our minds are wired. The idea that time must always have a before may be a deeply ingrained instinct, a quirk of human cognition, rather than a principle of cosmic truth. This dilemma begins with the simple fact that our brains operate inside time every waking moment. We move through our days in a neat sequence: morning before noon, cause before effect, decisions before consequences. Time is so deeply embedded in our experience that we instinctively apply it everywhere, like an all-purpose tool. If we see a tree, we imagine a seed. If we see a mountain, we imagine erosion. If we see the universe expanding today, we imagine a smaller universe yesterday. The idea of something without a prior cause feels unnatural, almost like reading a story that begins in the middle of a sentence. But the universe might not share our storytelling preferences. Many philosophical interpretations suggest that our insistence on asking what came before the universe may be a category error, like asking what color the number 7 is or what sound honesty makes. These questions feel sensible, but they unravel upon inspection because they mix concepts that do not belong together. Before the universe might be one such tangle, a pairing of ideas that only seems meaningful because our minds are shaped by temporal experience. One perspective comes from the notion that time is not a universal backdrop, but a feature of the universe itself. If time is part of the cosmic fabric, and that fabric began with the universe, then asking what came before time is like asking what lies north of the North Pole. The question dissolves not because the answer is hidden, but because the question reaches beyond the domain where its own terms are valid. The universe may not need a before any more than a circle needs a corner. This leads to a fascinating proposal. Maybe our urge to ask about beginnings is an evolutionary artifact. Humans developed in environments where identifying sequences, this happens because that happened, was useful for survival. If you can predict how events follow one another, you can plan, avoid danger, and make choices that keep you alive. Over millions of years, this instinct sharpened until it became a core feature of human cognition. We became creatures who think in timelines, whose thoughts flow like beads on a string, one after the other. So when we encounter a scenario with no sequence, no before, our minds rebel. They try to graft familiar patterns onto unfamiliar territory. Another philosophical angle suggests that the universe might not require an origin, because origins are human constructs. The notion of a starting point is part of how we organize experience, but nature might operate on principles that do not resemble our intuitions at all. Consider how we tend to imagine the universe with beginning-like metaphors: a spark, a push, a seed, a first step. These metaphors feel reassuring because they reduce cosmic complexity to human-scale stories, but they also risk limiting our imagination. The universe may not follow the logic of beginnings and endings. It might simply exist without requiring a first cause. Some thinkers argue that trying to apply human logic to the earliest universe is like trying to use a sundial in a dark room. The tool itself becomes inappropriate. Our logical structures evolved for landscapes, objects, and events within a familiar flow of time. When we step outside that flow into questions about origins or boundary conditions, we might be trying to measure something with the wrong instrument. Our minds try to map the infinite onto the finite, the timeless onto the timed, and the result can be confusion disguised as curiosity. There is also the possibility that our longing for a before stems from emotional roots rather than logical ones. Stories with beginnings feel satisfying. They give shape to existence. If the universe simply is, with no first cause or earlier version, that can feel unsettling, almost like a book with its first chapter missing. Humans crave narratives that unfold, progress, and resolve. But nature is under no obligation to provide a narrative that caters to human storytelling instincts. The cosmos might be stranger, simpler, or more indifferent than we imagine. Some philosophical interpretations even suggest that causation itself, our beloved chain of A leads to B, B leads to C, may not be fundamental. It might be a convenient overlay we apply to reality, rather than a law that reality follows. If causation is emergent rather than absolute, then asking about the cause of the universe's existence may be like asking why the ocean has waves instead of asking what caused the ocean itself. The question shifts the frame in a way that reveals its own limitations. In this view, the mystery of before the beginning is not a cosmic puzzle waiting for a clever solution. It is a mirror reflecting the structure of our thinking. The universe may simply be telling us in its vast, quiet way that not every question that feels natural is meaningful at the deepest levels. This does not make the question foolish, quite the opposite. It is one of the most profound questions humans can ask. But part of philosophical maturity is recognizing when a question invites us not just to look outward, but to look inward at the frameworks shaping our curiosity. The problem may not lie in the universe withholding answers. It may lie in the fact that our mental tools were forged in the middle of time, not at its boundaries. In this chapter, the mystery shifts from cosmic origins to human perception. The question, what came before, may reveal less about the universe and more about the architecture of the human mind, a reminder that the cosmos is under no obligation to follow the narrative patterns we find intuitive. Sometimes, the greatest mysteries point not only to the stars, but back at the way we ask about them. By the time we arrive at this final chapter, we have taken a long stroll through some of the most audacious ideas the human mind has ever dared to imagine. We have wandered through realms where time behaves like a direction you cannot travel, where universes sprout like cosmic bubbles, where branes crash like interdimensional bumper cars, and where the deepest foundations of space jitter with restless energy. And after all of this, after touring theories bold enough to make science fiction blush, one thing becomes beautifully clear. The universe is less like a tidy textbook and more like an ever-evolving story, with plot twists that would make even the most seasoned novelist raise an eyebrow. This is not a story with a single clean beginning or a neat ending. It is not a tale that ties all its threads into a perfect bow. In fact, the universe seems almost allergic to straightforward answers. Ask it a simple question. Where did everything come from? What happened before the beginning? Why does anything exist at all? And the universe replies with a shrug so cosmic it spans billions of light years. And yet somehow, that shrug is not disappointing. It is thrilling. You might expect that after so many theories and possibilities, the story would feel more complete. Instead, it feels bigger. The mystery has not closed. It has opened wider. Each idea we explored, whether grounded in physics or shaped by philosophical insight, is less a final answer and more a doorway to deeper questions. But this is exactly why studying the universe feels so intoxicating. It does not hand us conclusions. It hands us curiosity with a generous side of awe. There is something wonderfully humbling about this. Humans are an unusual species. We evolved to navigate forests and grasslands, to gather food, avoid predators, and tell stories around fires. And yet here we are, daring to question the nature of time, pondering dimensions we cannot perceive, and debating whether our universe is one of many or simply one chapter in a repeating cosmic cycle. We take the instincts we developed for survival and stretch them to their breaking point, using them to probe mysteries that existed billions of years before our planet formed. If curiosity were a superpower, humanity would be walking around with a cape. This curiosity is what transforms the unknown from something intimidating into something inviting. The universe may not always give us direct explanations, but it rewards curiosity with wonder. Those rare moments when we glimpse the enormity of reality and feel both impossibly small and enormously privileged at the same time. It is the sensation of standing on the edge of comprehension, aware that the next discovery might shift the ground beneath us. And what a plot the universe has given us so far. A cosmos expanding faster than we ever expected. A history written in faint microwave whispers. Galaxies swirling in structures so vast they make every human achievement look miniature by comparison. Particles flickering in and out of existence like cosmic stowaways. Black holes warping space-time until down and sideways become suggestions instead of rules. And through all of this, the universe remains a reminder that reality does not need our permission to be strange. What makes this strangeness rewarding rather than frightening is the growing realization that not understanding everything is okay. In fact, it might be the point. Mystery is not a flaw in the universe. It is a feature. If we understood everything, curiosity would have nowhere to go. The excitement of discovery would vanish. The universe would be a completed puzzle collecting dust, rather than a puzzle that keeps subtly changing shape every time we think we are close to finishing it. This does not mean the pursuit of answers is futile, quite the opposite. Every theory, every experiment, every question is another thread woven into humanity's long conversation with the cosmos. We explore because exploration is our nature. We ask because questions are how we illuminate the edges of understanding. And every time we uncover something new, the universe nods approvingly and reveals a little more of the next mystery waiting behind it. Even our biggest unanswered questions can feel like invitations rather than obstacles. What happened before time? What lies beyond what we can observe? Why does the universe behave like a storyteller with a fondness for dramatic reveals? These questions don't frustrate. They empower us. They remind us that the universe is not a solved equation, but a living frontier, always expanding both literally and figuratively. In the end, maybe the most meaningful message the universe offers is this: it is okay not to have all the answers. It is okay to sit with mystery. It is okay to marvel without fully understanding. Curiosity does not require closure. It thrives on wonder. And the universe provides wonder in abundance. So, as we step back from this exploration, consider the beauty of being part of a species that asks these wild, ambitious questions in the first place. Consider the thrill of knowing that mysteries far larger than ourselves still await discovery. Consider the delight of a cosmos that, despite its unimaginable scale, allows tiny beings on a small planet to ponder its deepest secrets. The universe may not hand us easy answers, but it delivers extraordinary plot twists, and somehow that is even better.